Hello, my name is Samuel Chen with Wolfram Research. Today I'd like to talk to you about financial statistics. We first obtain the financial data and achieve immediate visualization upon the data. Then we move on to descriptive statistics, distributions, probabilities, and finally multiple data sets. We can access financial data directly within Mathematica using financial data. Here we're asking for the monthly price of Dow Jones from 1995 to 2000. Instead of calculating the percentage change in price ourselves, we can simply ask Mathematica to return the fractional change. Notice we have 60 monthly prices and 59 monthly price changes. We can also ask for the most recent Dow Jones return and Dow Jones recent prices. And notice that we have 60 monthly prices along with 59 monthly price changes. We can use list plot to visualize the data. We can use box whisker chart to visualize the spread and shape of the data. Here's a box and whisker chart with outliers. Stem and leaf plot provides additional information about the data. Notice that the price changes include one value that seems to be the outlier. Obviously, this value return is real. We cannot disregard this data point. However, we can use this data point to demonstrate a simple statistical concept. That is, the difference between sample mean and sample median. Let's ask for the mean and median of Dow return. And we find the mean and median without the outlier. Notice the mean and median are much closer now, without the outlier. Therefore, the median is a better measure of central tendency because it is not affected by extreme values. We can find out the maximum and minimum of monthly price changes and the delta of the price changes. Let's arbitrarily set the return intervals at every 4%. Using bin counts, we can measure the absolute frequency and the relative frequency, the cumulative absolute frequency, and the cumulative relative frequency. Finally, these are the bins that we can place those values within. Let's use a table form to visualize our data. Financial data visualization with histogram is a must. Here, we ask for the histogram of Dow return. The tooltip returns absolute frequency. We can specify the bin width of the histogram. Here we're setting it to be 4%. We can also ask for the probability from the histogram. The tooltip values correspond to the relative frequency. Here we can ask for the cumulative count, and the tooltip values correspond to the cumulative absolute frequency. If we were to ask for the CDF from the histogram, the tooltip values correspond to the cumulative relative frequency. In Mathematica, the mode is represented with the command commonest. Now, what is the mode for Dow's price changes? We notice it has no mode. We can verify it using tally. Indeed, stock returns and other data from continuous distributions may not have a modal outcome. However, we can use histogram to find the modal interval. In Mathematica, the command quantile can be used to evaluate the quartiles, quintiles, deciles, and percentiles of data. Let's visualize the data above. We can apply what we can do with quantiles to our Dow's value. Here we ask for the members of Dow Jones, the market capitalization, the names of each corporation, and we can list plot them with tooltips. Here we ask for the PE ratio. Here we can use a manipulate command to create the user interface. Distributions with longer tails to the right have positive skewness. Distributions with longer tails to the left have negative skewness. The peakness of distribution can be measured by kurtosis. The normal distribution has kurtosis of 3. If the distribution has more kurtosis than normal distribution, it has a positive excess kurtosis. Here we show the excess kurtosis of 2 from the hyperbolic secant distribution. What about the skewness and kurtosis of the Dow's return versus normal distribution? Let's visualize the distribution. Notice here we're plotting the distribution of Dow's return from 1995 to 2000. Let's compare the skewness and kurtosis of the recent Dow return and visualize it. We can use the flip view command to compare our results interactively. To find the average monthly compound return, we need to use the geometric mean function. For instance, we ask the question, what's the average monthly compound rate for Dow's return? Let's verify the result. Here we're using the nest command to compound this particular return upon the Dow data from the first one to the last one. Here we asked for the last Dow data. Notice these results agree. The arithmetic figure is inappropriate. We can calculate average cost with harmonic mean. For instance, if an investor invests $10,000 in stock each month, and during the last 3 months the price per share was $27.1, $28.9, and $21, what is the average cost per share for the shares acquired? Let's check the result. Here we calculate the total shares purchased and find out the average price paid. Notice the results agree with harmonic mean. Let's define 5 stocks and your annual returns. The mean of the return. The mean absolute deviation can be defined with this formula. In Mathematica, we can use the built-in function mean deviation to find the mean absolute deviation. Therefore, on average, the individual return will deviate mean absolute return from the mean return. Of course, the variance and standard deviation can be calculated easily. The coefficient of variation can be defined with this formula, where S of x is the standard deviation and x bar is the mean. Coefficient of variation is a relative measure of dispersion. In our case, it measures the risk per unit of expected return. Let's obtain the monthly return of NASDAQ and Apple. Define a function for coefficient of variation, and find the coefficient of variation for NASDAQ and Apple. We can use a paired histogram to visualize the result. The Sharpe ratio is a risk-adjusted financial measure. It is defined by this formula, where R bar is the mean return of the portfolio, RRF is the risk-free return, and sigma is the standard deviation of the fund's return. Let's take a look at the 3-month Treasury bills return in January 2000 and use that as a risk-free return. Let's take a look at our mean of Dow return. Okay, write a little formula to define the Sharpe ratio. In the Sharpe ratio of Dow return, given 5.76% of 3-month Treasury bill in January 2000 is negative 0.88. That means that Dow lost 0.88% excess return per unit risk. Instead, let's take a look at the most recent Dow return. Here we ask for the 3-month Treasury bill return. Now we can use the Sharpe ratio formula that we have defined above to ask for the Sharpe ratio of recent Dow return. Therefore, up to October 2011, a 5-year Dow portfolio lost 0.015% excess return per unit risk. Logistic distribution provides very good fit for fractional price changes from the previous closing price of stocks. Using estimated distribution, we find the parameters to the logistic distribution. Let's compare the histograms. We can use a random variate command, ask for the number of simulated data points based on the estimate distribution. We can visualize the simulation. The expected value for a finite number of outcomes is the weighted average of the possible outcomes of a random variable. It is defined by this formula. The weights are the probabilities that the outcomes will occur. We can understand the expected value in the coin tossing game. Say we get $1 if the coin lands on its tail, and we get nothing if it lands on heads. Here is the result of 10 tosses. And the expected value is $5, as expected. Returning to our Dow example, we can use expectation and ask for the expected return of the Dow if the monthly returns indeed follow the estimated logistic distribution. Now that we know the expected value of the Dow return, we can ask Mathematica for the probability of the Dow generating a return of 3% or greater. Similarly, we can ask Mathematica the probability of making $2 to $8 from a coin tossing game. Here we show the tree form of Bayes' formula. What this tree shows is that there is a 60% probability that the economy will outperform. If it does, there is a 70% chance the stock will go up and 30% chance the stock will go down. There's a 40% chance the economy will underperform. If it does, there's a 20% chance that the stock in question will increase in value and 80% chance it will not. Notice the possibilities of all four outcomes add up to 1. In terms of the updated probability, we'd like to ask the question, given that the stock has gains, what is our updated probability of an outperforming economy? Manually, we can sum the probability of a stock gains in both states to get 50%. Given that the stock has gains, the probability that the economy has outperformed is 84%. Or we could define the probability this way. We can also use the built-in function empirical distribution to perform the manual calculation. Notice results agree. We're often interested in the relationship between two data sets. Here we obtain the annual returns of S&P 500 and the Wilshire 2000. We verify the dates match, and we place our data in the grid. We can visualize our data as a time series. But let's find out the relationship between the observations. Here we can call for the core data and ask for the correlation. If we only need the correlation coefficient, we can use the part command to take the coefficient of correlation from the correlation matrix. Or we can place the data of interest inside a correlation command. The best way to visualize the relationship is to use a scatter plot. In Mathematica, a list plot is used. Here we insert tooltip. Let's generate a scatter plot of the daily returns of S&P 500 versus Wilshire 2000. We can also find the correlation. Notice the correlation of daily return is weaker than the correlation of annual returns. Linear regression allows you to use one variable to make predictions about another. Test hypotheses about the relationship between the two variables, and quantify the strength of the relationship between two variables. Here we take the annual returns of both S&P and Wilshire, and we're trying to perform a linear regression upon them. We give the linear regression relationship right here. In Mathematica, the function linear model fit fits a linear model and returns a fitted model object containing information about the fitting. For instance, we can ask for the normal expression of the model. We can use plot and list plot to visualize the data and its linear fit. Many times we need information about the fitting. For instance, we can ask the model for its fit residuals, plot them, and we can visualize the residuals on top of the original data. The y-intercept means that if S&P 500 returns 0% in any particular month, the returns on Wilshire 2000 will be 0.07%. Notice the slope is the covariance of the variables divided by the variance of the independent variables. The standard error of estimate is given right here. We can simply ask for the square root of the estimated variance. The standard error of estimate gives some indication of how certain we can be about a particular prediction of y using the regression equation. We often use the coefficient of determination r squared as an indication of how well the independent variable explains the variation in the dependent variable. Here we ask for the r squared within our model. Therefore, 90.8% of the variation in the Wilshire 2000 annual return is explained by variation in the S&P 500's annual return. Since we have a linear regression with one independent variable, we can also use the square of the correlation coefficient to obtain r squared. Analysis of variance is a statistical procedure for analyzing the total variability of a set of data into components that can be attributed to different sources. Here we can ask for the ANOVA table from our fitted object. In our case, notice the F statistic is not small. It seems that the regression model does a good job of explaining variation in the dependent variable. Notice also that the p-value is fairly low. Therefore, the probability that the true value of this slope coefficient is actually 0 is small. In this talk, we have walked through a process of obtaining financial data and perform an immediate statistical analysis on the data. There are many other aspects of financial analysis and valuation that we have not discussed. We welcome you to explore these topics at a later time. Thank you.